Hello, I hope all of you are doing well. So I welcome you to the day 4 of this course. So we stopped in the last class after finishing the mirror plane symmetry and we just started the center of inversion. So we'll start from there itself, okay. So what is the symmetry of inversion, or also known as center of symmetry, inversion symmetry? So inversion symmetry is a point, okay, and this point may not contain any atom if I consider a molecule. So if I take any point on any part of the molecule and pass it through that particular point and go equal distance on the other side, I will find an equivalent point, and then this center point or origin through which I am passing is known as center of inversion. Let me take an example, okay. So I showed you this model in the previous class. This is of benzene, right? Now you can look at this molecule, pick up any hydrogen atom here. So I am picking up an hydrogen atom right here. Then I am passing through the center of this molecule, okay, the center of mass of this molecule, and then going equal distance. What I am finding? I am finding another hydrogen, okay. So this is just equivalent to the previous hydrogen, and I take anything. I take this point particularly, okay. I take this point and pass through this central point again. I get another similar point over here. So similarly, you take point anywhere on this molecule, okay. You pass through this point at the center and walk the same amount, same distance, you will find exactly a similar point on the other side. So this point here, the center for this particular molecule, will be the inversion symmetry point, okay, or the center of inversion. So you you can take many other molecules. Let me show you another example. So this particular model that you can see if it is zoomed a little bit more, then this is a model for ethylene, okay, C double bond C and then 4 hydrogens here. So you suppose you mark here 1, 2, 3, 4, then you take 1 and you start walking, reach this midpoint of this CC bond, and then keep going in the same direction by same amount, you will reach here, right? So similar thing will happen for this hydrogen. This will reach here, and the other one sitting here will come here, correct? So if I have started with A, B, C and D, then A will go to the position of C, C will go to the position of A, and B will take the position of D, and vice versa. So I have to start with A, B, C, D. Now after having this inversion symmetry, I have C, D, A and B, okay. So this point at the center of CC bond in this particular molecule is the inversion symmetry or center of inversion, okay. So if you like in the last class toward the end, I told you that, okay, if I consider any point on a molecule which possesses a center of inversion, then you consider any given point. Not necessarily you have to consider an atom, but you can consider any point on in a given bond, okay. You will find the exactly same point on the other side of the molecule once you pass through that center of inversion, okay. So now if you consider the screen that is being played in front of you, I take another example of an octahedral molecule, okay. So you can take this molecule like any transition metal complex, like CO H2O whole 6, okay, ignoring the metal charge. So this will form an octahedral complex. So all the CO bonds Okay, and if I take this OH as a like a ball, so each of the ball is like OL, or you can take it like COCl6, cobalt chloride hexachloride. So each of these is, you can take it as a chloride chlorine atom. Okay, and the central is a metal CO, cobalt. Now they will occupy an octahedral geometry, right? So they will all the chlorine atoms will be disposed at all 6 vertices of an octahedron. So we have marked here like 1, 2, 3, 4, 5, 6. So 1 and 6, they are occupying the axial positions, while the chlorine atoms at 2, 4, 3 and 5, they are in the equatorial plane. Now all the CO-Cl bond distance are equal. Now having that in mind, you start from chlorine 1, okay, and we have a point right here, the center of this cobalt atom. Okay, now if we start from this chlorine 1 and keep walking through this bond and come here to this point and then keep going in the same direction and equidistance, then we end up having a chlorine, finding this 6 chlorine atom. Okay, so similar thing will happen for 3. 3 will go to the place of atom 5, 2 will come to the position of 4, and 4 will go to the position of 2. Okay, so 5 will come to the position of the 3rd chlorine atom, and 6 and 1 will interchange their position upon this inversion symmetry operation. So what will be the structure? Structure is shown here in this, right? So you can see, I said 1 will go to the place of 6 and 6 will come to the position of 1. That's what exactly is happening, right? 6 and 1, they are interchanging their position. So whenever you have a center of inversion and you want to operate that particular operation on any given molecular structure, the rule of thumb is all the atoms or bonds which are disposed on 2 different sides of this particular point in the space, they will interchange their positions, right? So we can see here 2, 4, 3, 5, 1, 6, they are all interchanging their position. So knowing this, we should be able to write the structure of any molecule after operating inversion symmetry operation, if the molecule possesses a center of inversion. You cannot operate any symmetry operation on a molecule which doesn't have it, right? So for example, we talked about this CHCl3 chloroform, right? So in case of chloroform, do you think there is a center of inversion? The answer is no, because there is no such point through which I can pass and reach an equivalent point on the other side. Okay, suppose I want to start from this hydrogen, I will not find another hydrogen on the other side if I even consider any point. So there actually is no such point in this particular molecule which can invert its structure. Center of inversion, this symmetry operation, actually inverts its structure. Okay, so this molecule doesn't have one, but the other 2 molecules that I showed you, that benzene and ethylene, they have a symmetry operation known as center of inversion. Now here on your screen you can see that I have tried to compare this inversion symmetry with another similar kind of symmetry operation, that is rotational symmetry of order 2, that is by using a C2 axis. Okay, so I have a molecule exactly the one that I showed you earlier, that is ethylene. Okay, so I have an ethylene molecule. So if you look at the screen, you can see that all these hydrogen atoms of ethylene, they are marked by A, B and C and D, and then we can perform this symmetry operations I or the C2 on these 2 structures. So here clearly I, that is inversion operation, will invert the structure. So A will go to the position of D and vice versa, and so will this B and C will interchange their position. So you will ultimately get this particular structure upon inversion symmetry, inversion operation. Now C2, on a first glance, it gives you a feeling that it will end up doing the same thing, but will it really do that? Let's have a look at it. So if you look at on your screen, you can see that a C2 axis, which is in the plane of the molecule. So this C2 is not perpendicular to the plane of the molecule, but it is in the plane of the molecule. So what will happen? This C2 will make a rotation of 180 degree. So this A will now go to this place, C will go to this place, and the others will come here and here. So I should have a structure like this, correct? So though apparently I and C2 you can think that okay, they are similar, but you can see these two structures, when I mark them with A, B and C and D, you can see that they end up in two different structures. But if I forget about A, B and C, D, this marking, then these two structures are equivalent, right? So they are indistinguishable in that sense. All right. So that's about the inversion symmetry. So here also I will suggest you to take some molecules, particularly the molecular model, and you try to look at the inversion symmetry points, okay, the center of inversion in that given molecule. So more you practice to find out about the symmetry elements, it will be more better for you. So let's move to the next symmetry element that we need to learn. So the next symmetry element is known as improper axis of rotation. So this is a symmetry element which is whose symbol is Sn, S subscript n. So now we have something called improper, because initially we started with proper axis of rotation, and I told that okay, find the meaning of this proper, this term will be clear, it will be more clear when I discuss something which is improper, and here we come. So the name itself suggests that okay, probably there is no such existence of an axis in reality. Okay, let's have a look at it. What does it mean? So let's look at the definition of this improper axis of rotation. So this improper axis of rotation, if I think about this particular operation first, so this operation is not a single operation, but this is a combination of two operations, one rotation and one reflection. Okay, so you take a molecule, you can find an axis which actually may not be one of these CNs. That means it may not be along any proper axis of symmetry. Now you suppose you find such an axis about which you can have a certain degree of rotation followed by a reflection on a plane which is perpendicular to that previous axis of rotation, and you end up getting an indistinguishable structure. Then this axis that you chose will be called an improper axis of symmetry, okay, or improper axis of rotation. And as I said, it doesn't necessarily mean that this particular axis will also coincide with a proper axis of rotation, and that is why it is called improper axis of rotation. So essentially, if I can write this Sn operation, I should write it in this way. So Sn, this is an improper axis of rotation, improper axis of rotation. Okay. So, this ascent is first a rotation operation followed by an reflection, and this reflection is such that this plane, sigma plane, is perpendicular to this Cn. Okay. So, I can write this is a perpendicular, okay, perpendicular to this Cn. Okay. Many occasion you will find in many books that this is written as sigma h, which may not be grammatically correct, because as I said, this improper axis of rotation may not be along the proper axis of rotation. So, sigma h is defined with respect to the proper axis of rotation, okay, the principal axis of symmetry. Now, if I have a perpendicular plane to that axis of rotation that I am talking about for Sn operation, and if this Cn does not lie in the same direction as that of the principal axis of rotation, then this sigma cannot be called as sigma h, even though it is perpendicular to this axis. So, in general I will call it like a sigma perpendicular. Okay. So, Sn is an operation which is done in this way, Cn followed by a sigma plane, and that will return you an indistinguishable structure. Let us take one particular example, okay, so that it is clear to you. So, here on your screen we have a molecule called methane. Okay. So, this is not a model for methane though. So, now let us concentrate on the molecule that is on your screen right now. So, you look at this molecule methane and consider an axis which bisects two HCH angles simultaneously. Okay. So, if I can show you that, then it will be probably much better. So, I will show you using a model. So, this is what is shown on your screen. So, now if you look at on this particular model, which is a model for methane, so you can see all red sticks represent the CH bonds. Now, you can hold this molecule like this, where you can see this C3 axis, principal axis of rotation, but at the same time you can find a C2. So, C2 will be like this, like one axis passing through the middle of this angle, right. So, you can see this angle, if you orient it in such a way that you can see only one CH bond, because the other one is just blocking the other CH bond, and then this axis obviously will cut this angle into half. So, essentially this axis is cutting this angle and this angle into halves. So, there if I give a rotation, it becomes like this. So, 120-degree rotation will give you an indistinguishable structure. So, that is a C2. Now, that is fine. Now, can I imagine an axis through this one which will be an improper axis of rotation? Answer is yes. How? So, look at this properly. So, I am using that same C2. Okay. I took an example which will be very easy to follow. We can go to much complex structures as we progress, and for the time being I showed you the C2 so that you can actually identify this Sn axis here also. So, I take an axis through the same C2 axis here. Now, instead of giving a C2 rotation, I give a rotation by 90 degree. So, what I do is about this axis I give a 90 degree. So, if I give a 90 degree rotation, this will go toward you, right, all right. So, now I imagine a plane which is perpendicular to this axis. So any reflection will bring this molecule here, this atom here, and this angle will be like this now, and this bond will be coming like this. Okay, this will now go here, and this bond will now go here, because I am reflecting on a plane which is situated here. So that will make the structure like this. Now if you just return to the this video couple of minutes back, then you will see we started with this structure. So what does that mean? I could find an axis and a particular angle of rotation by which I can turn the molecule to a structure which is not indistinguishable, which is very much distinguishable. But then if I give a reflection perpendicular to that axis, then I get an indistinguishable structure. So this combined effect of a rotation followed by a reflection perpendicular to this axis gives me an indistinguishable structure. Now if you go back to the original definition of a symmetry operation, we said clearly that movement of a body which produces an indistinguishable structure. So obviously here this operation, a rotation followed by a reflection perpendicular to the rotational axis, if it gives an indistinguishable structure, this is a symmetry element, a symmetry operation. Okay, and this all together Cn sigma perpendicular, as we showed here, this all together forms the symmetry operations, and that is denoted by Sn. So here I will also mention that many times I am going back and forth between these two terms, symmetry operations and symmetry elements. I have discussed what is what in my first or the second class. So you should not be confused about the symmetry element and symmetry operations, and both symmetry elements and symmetry operations are symbolized by the same letter. So here this Sn, if I can find out, suppose for this particular molecule I will call this axis as an Sn axis, and then I can use this Sn to symbolize an Sn operation. Okay, and then once I use it as an operation, I change the molecular structure to another indistinguishable, change the molecular structure to another distinguishable one. Okay, so you have to practice a lot to find out if a molecule has an improper axis of rotation. So now on your screen right now you have an example of generalized example of some Sn axis. So this n is the order of rotation. Okay, it's pretty much similar to what we had in case of proper axis of rotation. So Sn, where n equals to 1, it would mean a 360-degree rotation, right? And S2 would mean 180-degree rotation, S3 would mean 120-degree, and so on. And in every case, it is implied that the rotation about that particular angle followed by a reflection into a perpendicular plane. So when I talk about S1, okay, so S1 is C1 followed by sigma perpendicular. C1 is nothing but identity, so C1 does not do anything, and then we are left with a sigma perpendicular. So if there is any reflection perpendicular to this C1 axis, if there is a axis I imagine, then essentially S1 means nothing but a reflection. So if you see anywhere that somebody has used an S1 operation, S1 is nothing but a operation by a plane of symmetry. Okay, so it's just a reflection on a plane. Now come to S2. This is interesting. S2 is like you look at the screen and suppose a molecule has an S2. So what does mean? So I will rotate by 180 degrees. So whatever was on this side, it will now come back to this side, correct? Because it's an 180 degree rotation. So it is at, this part will come here. Now if I give a rotation, what will happen? So now after the C2 it has come here. Now after the reflection on a perpendicular plane, it will go here, down here. So essentially these two operations, it produces, it actually inverts the position of this object which we started with. Okay, so it goes over here. So that means it will have an center of inversion. So S2 is necessarily inversion, which exactly is shown here. So we start from this particular point, give a 180 degree rotation, and then we reflect it here. Now I could easily get it through an inversion symmetry here. Okay, so S2 is nothing but center of inversion. Okay, so you can go to a higher one like S3 if you look at. So that will have a C3 followed by a sigma perpendicular. S4, as we showed with this methane molecule, it will have C4 followed by sigma perpendicular, and so on. Okay, so you can try to look at different molecular models and try to find out what are the different symmetry elements. So by now I have showed you pretty much all the symmetry operations, symmetry elements, and the symmetry operations that you can have in a given molecular structures. Now you should try finding out all those symmetry elements that are possible in a molecular structure. Okay, so we have come to the pretty end of this particular lecture. So we have learned so far all the symmetry elements and symmetry operations, and we tried to find out some of the symmetry elements from some of the molecules. Now in the next step, our intention is to find a quantitative way so that I can say, we can talk about the nature of symmetry of a given molecule, if one is higher symmetry than other or not, and we should be able to utilize these symmetry elements present in a molecular structure in a proper way that can actually help me having applications of this symmetry elements and operations. So for that we need a mathematical framework, which is actually a group theory. Okay, so in the following class we will try to learn what group theory is, a basic mathematical concept of group theory, and then in the following classes we'll try to see how this symmetry is being assimilated into the group theory, and how it helps us in solving various problems in chemistry. Thank you very much for your attention. See you in the following class.